In this video, I'm going to show you how to solve problems involving pressure, temperature, volume, and number of moles of a gas when they're changing. Now, in these problems, sometimes you'll see the words standard temperature and pressure, or STP. And you need to know that standard temperature and pressure occur when the temperature of a gas is at 0 degrees Celsius, or 273 Kelvin, and when the pressure is 1 atmosphere, or 760 millimeters of mercury, or 101.325 kilopascals, or 14.7 pounds per square inch. These are all equivalent to each other. And again, sometimes we just refer to this as STP. In these problems, you'll always work the problem in Kelvin. So if you have degrees Celsius, be sure to add 273 degrees to it. If the problem asks you for a final answer in degrees Celsius, after you get your answer in Kelvin, to get back to degrees Celsius, just subtract 273. Look at example problem number 1. You buy a 3-liter helium balloon in the mall and place it in a car sitting in hot summer sunlight. The temperature in the air-conditioned mall was 22 degrees Celsius, and the temperature inside the closed car is 45 degrees Celsius. The question is, what will the volume of the balloon be in the hot car? So what we'll do is take these three values and I'm going to place them in this chart here. Notice when I put in the temperatures, I'm going to put them in as Kelvin temperatures. Here I've put in the initial volume of the balloon and its initial temperature in the mall, the temperature of the hot car. I put a question mark where it says, what's the new volume? And notice how I crossed off pressure and number of moles because those aren't going to be changing. Now, remember that when the temperature gets hotter, the volume is going to go up because temperature and volume have a direct relationship. So we'll use this knowledge to solve the problem. I started by writing down the original volume of the balloon. Now we'll multiply by a ratio of temperatures such that we get a larger volume after multiplying by that ratio. So to get a ratio larger than 1, take the larger temperature and put it over the smaller one. There's our ratio. Now after multiplying 3 times 318 divided by 295, we'll get our answer of 3.2. Notice that I wrote the answer with 2 significant digits and a unit because I started with 2 significant digits with my original volume. If I were to draw a depiction of this phenomenon, here's a picture of my balloon with a couple of gas particles in it that are moving at a fairly slow rate because they're in a cold mall. And now I'll draw that balloon bigger. I'll be sure to put the same number of particles in, but they're moving faster, so I'll give them a few more whooshies. And that's a picture. This next problem is a little bit more complex because we're going to have 2 variables changing instead of just 1. A small research submarine with a volume of 1.2 times 10 to the 5th liters has an internal pressure of 1 atmosphere, so I'll put that pressure here, and a temperature of 15 degrees Celsius. I'll put that temperature here, but I'll be sure to add 273 to it. The submarine descends to a depth where the temperature is 3 degrees Celsius. Again, I'll put that temperature here, but add 273. And the hull of the submarine breaks. If the gas inside the broken submarine now occupies a volume of only 767 liters, what is the external pressure on the air deep within the ocean in atmospheres? In the next slide, I'll show you all of these variables placed into this table. Here you see the original pressure, a question mark next to the final pressure, the 2 temperatures, original and final, having added 273 to them, the original volume and the final volume. Now, note in these bottom boxes, I'm interested in knowing how the change in temperature affects the pressure. Temperature and pressure are directly related, so if the temperature went down, the pressure will go down. Volume and pressure are inversely related, so as the volume goes down, the pressure goes up. I put an X on the moles because the number of moles of gas are not changing. To start this problem, because I'm solving for pressure, I'm going to start with my original pressure. Next, I'm going to multiply by a ratio of temperatures such that my pressure will go down. So to get a fraction less than 1, I'll put the smaller k value on the top of my fraction, 276 over 288. For my volume ratio, I want to make sure that I write a ratio such that that causes the pressure to increase. So this time I'll put the larger value on the top so I get a fraction larger than 1. Okay, now I just do the math. 1 times 276 divided by 288 times 1.2 E5 divided by 767 should give me a final answer of 150 ATM I wrote this with 3 significant digits, and notice I needed to put the decimal there to make that 0 significant. So to draw a picture of this, I might draw my original submarine with my gas at a slightly warmer temperature, and then the volume significantly decreases, so I'll draw a smaller box, but my particles of gas have gotten colder, so I have fewer whooshies there. And that's it. So you're going to try these problems in section 11D, I believe. And if you feel like there's not enough numbers for you to use, it's probably because you're using standard temperature and pressure. So remember, standard temperature is 0 degrees Celsius or 273 Kelvin, and standard pressure is 1 atmosphere. Good luck, and just ask me a question if you have any.